Earth, as it exists today, is a planet defined in large part by its ice. The polar ice sheets of Antarctica and Greenland, the glaciers threading through mountain ranges, the seasonal sea ice expanding and contracting across the Arctic Ocean. These are not incidental features of the planet's surface. They are structural. They regulate temperature. They influence ocean circulation. They reflect solar energy back into space, and they hold within them an enormous proportion of the planet's fresh water. To most observers, ice feels permanent. It feels like a given. But in the full context of Earth's history, ice is the exception, not the rule. The geological record, preserved in rock strata, sediment cores, chemical isotope ratios, and fossil assemblages, tells a different story from the one that modern landscapes suggest. For the majority of Earth's 4.5 billion years of existence, the planet carried little to no permanent ice. The polar regions were not frozen wastelands, but warm, humid environments. The deep ocean floors were significantly warmer than they are today. The atmospheric and oceanic systems that now depend on the presence of ice operated under entirely different parameters. This was not an anomaly. It was the baseline condition of a planet that, for most of its history, ran warmer than anything recorded in human experience. Before we go further, this journey takes us across deep geological time, through climates and landscapes that no human has ever witnessed firsthand. Where in the world are you watching from tonight? Geologists and climatologists refer to these extended periods of warmth as greenhouse climates, intervals characterized by elevated atmospheric carbon dioxide concentrations, minimal glaciation, and global mean temperatures substantially higher than present values. The most recent and well-documented of these prolonged warm intervals is the Eocene epoch, spanning roughly 56 to 34 million years ago. At its peak, during the early Eocene climatic optimum, global mean temperatures are estimated to have been approximately 10 to 15 degrees Celsius, warmer than today. These figures are not speculative. They are derived from proxy evidence, from the oxygen isotope composition of ancient foraminifera, from the distribution of temperature-sensitive plant fossils, and from the preserved chemistry of deep-sea sediment cores drilled from multiple ocean basins across the globe. What those figures represent, translated into physical reality, is a planet that would be almost unrecognizable to a modern observer. The coastlines were different. The interiors of continents were different. The air carried more moisture and more carbon dioxide. The distribution of life across latitudes, from the equator to the poles, followed patterns that have no precise modern analogue. Understanding this world requires setting aside the assumption that Earth's current configuration is typical or permanent. It is neither. It is the product of a long and still ongoing cooling trend that began tens of millions of years ago, shaped by forces operating at geological scales of time. To place this in context, it helps to consider just how much of Earth's timeline has been spent in a warm, ice-free state. Current scientific estimates suggest that for roughly 85% of the past 500 million years, the period during which complex multicellular life has existed on land and in the sea, Earth's climate was warmer than it is today, with little to no permanent ice at the poles. The ice ages that punctuate more recent geological history, including the one we are technically still within, represent a relatively narrow slice of time. They are the product of specific conditions that aligned over millions of years, not the default state of a living planet. The premise of an ice-free Earth is therefore not a thought experiment. It is a documented historical reality. It's supported by multiple independent lines of evidence drawn from across scientific disciplines. Stratigraphy reveals the absence of glacial deposits during these warm intervals. Paleobotany documents the presence of frost-sensitive plant species, palms, tree ferns, and broadleaf tropical vegetation at latitudes that today sit well within the Arctic and Antarctic circles. Geochemistry records the elevated carbon dioxide levels and altered ocean chemistry that sustained these warm states across millions of years. Each line of evidence, assembled independently, converges on the same conclusion. There have been long stretches of Earth's history during which ice, as a dominant and structurally significant planetary feature, simply did not exist. Understanding why this matters requires appreciating the role that ice plays in Earth's current energy balance. Ice is highly reflective. When sunlight strikes an ice-covered surface, a large proportion of that energy is reflected back into space rather than absorbed. This property, known as albedo, is one of the primary mechanisms by which the polar regions regulate global temperature. Remove the ice, and that reflective surface disappears. The darker ocean and land surfaces that replace it absorb significantly more solar energy, which in turn drives further warming. This feedback relationship, where warming reduces ice and reduced ice causes further warming, is one of the reasons that ice-free climates, once established, tend to be self-sustaining over geological timescales. During the Eocene, this feedback was in full effect. With no significant polar ice sheets to reflect incoming solar radiation, the planet absorbed more energy across a larger surface area. Ocean temperatures at high latitudes were warm enough to support subtropical marine life. Rainfall patterns extended deep into continental interiors. The thermal gradient between the equator and the poles, which today drives much of the planet's atmospheric and oceanic circulation, was substantially reduced. Weather systems, ocean currents, and biological productivity all responded to these altered conditions in ways that produced an Earth fundamentally different from the one that exists now. The transition from an ice-free world to a glaciated one did not happen instantly. It unfolded over millions of years, driven by the slow interplay of tectonic movement, changing ocean gateways, and declining atmospheric carbon dioxide, and shifts in Earth's orbital parameters. The opening of the Drake Passage between South America and Antarctica, which allowed the formation of the Antarctic Circumpolar Current, is considered one of the key tectonic events that contributed to the thermal isolation of Antarctica and the eventual formation of its ice sheet. Atmospheric carbon dioxide levels, which had been elevated throughout the Eocene, began a long decline that progressively reduced the greenhouse effect sustaining the warm climate. These changes accumulated gradually over timescales far beyond the scope of human perception. But before that transition began, before the planet entered the long cooling trajectory that would eventually produce the ice sheets, the glaciers, and the frozen poles we recognize today, the Earth sustained conditions of remarkable and enduring warmth. The systems that maintained that warmth, the biology that evolved within it, and the structural differences between that world and the present one form a coherent and well-evidenced scientific picture. It is a picture assembled from rock and chemistry and fossil, from cores pulled out of the ocean floor, and from outcrops exposed by erosion across every continent. What follows is an account of that world, constructed not from imagination, but from the physical record the planet itself has preserved. The phrase ice-free Earth carries an immediate visual implication, the absence of something. But to understand what an ice-free planet actually represents, it is more accurate to think not in terms of absence, but in terms of replacement. Every condition that ice currently maintains, every system it currently regulates, every boundary it currently defines, all of it was occupied by something else. warmer water, warmer air, higher coastlines submerged beneath expanded seas. A planet without ice caps was not a planet missing a feature. It was a planet operating under an entirely different set of physical parameters. The most immediate and measurable consequence of a fully ice-free Earth is sea level. Today, the ice sheets of Antarctica and Greenland together hold enough frozen water that, if fully melted, would raise global sea levels by approximately 65 to 70 meters above their current position. During the Eocene, when no significant continental ice sheets existed, sea levels reflected this absence. Paleoceanographic reconstructions estimate that Eocene sea levels stood somewhere between 50 and 100 meters higher than today, depending on the time interval and the specific proxy data used. The uncertainty in these figures reflects the complexity of reconstruction across deep time, but the general magnitude is well supported across multiple independent datasets. What a 70-meter rise in sea level means for continental geography is substantial. The shallow coastal margins of every continent would have been inundated. Large portions of what are now interior landmasses, the central plains of North America, the lowland basins of Europe, and the broad flatlands of Asia would have lain beneath shallow inland seas. The continents themselves were smaller in their exposed surface area, their edges softened and submerged, their interiors in some regions accessible to warm, shallow marine environments that penetrated hundreds of kilometers from the modern coastline. These epicontinental seas, as they are known, were not deep ocean environments. They were warm, nutrient-rich, biologically productive bodies of water sitting atop what are now dry plains and agricultural landscapes. The shape of ocean basins was also different. Tectonic activity over the intervening tens of millions of years has continued to shift the positions of continents, alter the depths of ocean floors, and open or close the gateways through which ocean currents flow. During the Eocene, the configuration of the continents produced ocean circulation patterns with no modern equivalent. The Tethys Sea, a vast warm body of water that once stretched across what is now the Middle East, Southern Europe and Central Asia, was still partially intact during the early Eocene, connecting the Indian and Atlantic Oceans through a low-latitude corridor. This connectivity allowed warm tropical water to circulate more freely across the globe, contributing to the relatively uniform warmth that characterized the period. Beyond sea level and ocean configuration, the thermal structure of the atmosphere was fundamentally altered. Today, the temperature difference between the equator and the poles, the meridional temperature gradient, is one of the primary drivers of atmospheric circulation. Cold polar air and warm tropical air interact along frontal boundaries to generate the jet streams, storm tracks, and seasonal weather patterns that define climate across the mid-latitudes. In the Eocene, with polar regions that were warm rather than frozen, this gradient was significantly reduced. Climate models and proxy reconstructions consistently indicate that Eocene polar temperatures, particularly at the surface, were far higher than their modern counterparts, with some estimates placing mean annual temperatures in the high Arctic above 10 degrees Celsius compared to the -20 or colder averages seen today. A reduced meridional gradient does not mean a calm or featureless atmosphere. It means a differently organized one. Storm systems, precipitation patterns, and the distribution of wet and dry zones across the continents all responded to the altered thermal structure. Evidence from fossil soils, pollen records, and sedimentary deposits indicates that rainfall during the Eocene was broadly distributed, with humid conditions extending into regions that are today arid or seasonally dry. The monsoon systems that now dominate tropical and subtropical climates likely operated under modified dynamics, and the seasonal extremes familiar from modern mid-latitude climates were less pronounced across much of the globe. The deep ocean, too, was structured differently. Today, deep ocean circulation is driven in significant part by the formation of cold, dense water at the poles. Water that sinks and spreads along the ocean floor, carrying oxygen and nutrients into the deep sea. This thermohaline circulation, sometimes described as a global conveyor belt, depends on the temperature contrast between polar and tropical waters. In the Eocene, with polar seas that were considerably warmer, the density contrast driving this circulation was reduced. Evidence from deep-sea sediment cores suggests that bottom water temperatures during the early Eocene were significantly higher than today, and that deep ocean oxygen levels may have been lower in some regions as a result of reduced circulation. The chemistry and biology of the deep ocean operated under conditions quite different from the cold, well-ventilated abyssal environment that characterizes the modern seafloor. Atmospheric carbon dioxide concentrations during the Eocene are estimated, through various proxy methods, to have ranged from approximately 500 to over 1,000 parts per million, compared to the pre-industrial modern value of roughly 280 parts per million and the current value of over 420 parts per million. These elevated concentrations were the primary driver of the greenhouse warming that sustained the ice-free climate. Carbon dioxide absorbs outgoing infrared radiation and re-emits it in all directions, including back toward the surface, a mechanism that, at higher concentrations, produces a measurable and well-quantified warming effect. The Eocene demonstrates, across millions of years of geological evidence, what Earth's climate system produces when carbon dioxide concentrations are sustained at high levels over geological timescales. It is worth noting that the Eocene ice-free state was not the result of any single cause operating in isolation. It was the product of a convergence, elevated greenhouse gas concentrations, a tectonic configuration that permitted broad ocean heat distribution, the absence of the reflective feedback that ice provides, and atmospheric circulation patterns that spread warmth more evenly across latitudes. These factors reinforced one another, producing a climate state that was stable enough to persist for millions of years. Stability in this context does not imply the absence of variability. Within the Eocene, there were shorter intervals of relative cooling and warming, fluctuations in carbon dioxide, and transient events of significant climatic disruption. But the overarching state, warm, ice-free, high sea level, persisted across the full duration of the epoch. What the geological record of an ice-free Earth ultimately reveals is not a bizarre or extreme deviation from normal planetary behavior. It reveals a climate system operating within a different but internally consistent set of boundary conditions. Remove the ice, raise the carbon dioxide, alter the ocean gateways, and the physics of the atmosphere and ocean produce a coherent and documentable result. The Eocene is not an outlier in Earth's history. It is, by the measure of deep time, closer to the norm. The physical geography of an ice-free Earth was not simply a warmer version of the world that exists today. It was structurally distinct, shaped by different coastlines, different atmospheric circulation patterns, different soil chemistry, and different biological communities occupying every terrestrial zone from the equator to the poles. To reconstruct these landscapes, paleontologists, paleoecologists, and geologists draw on a convergence of evidence. Fossil pollen preserved in ancient lake sediments, the chemical signatures of paleosols, fossil soils, the distribution of plant macrofossils across rock formations, and the isotopic records stored in ancient wood and leaf material. Together, these sources produce a picture of terrestrial environments that were, in many regions, radically unlike anything present on Earth today. The most striking feature of Eocene terrestrial geography was the extension of dense, humid forest into latitudes that are today dominated by tundra, permafrost, and polar desert. Fossil evidence from sites in the Canadian Arctic, Svalbard, Alaska, and Antarctic coastal regions documents the presence of diverse, warm temperate to subtropical vegetation at latitudes above 60 and even 70 degrees. These were not sparse or stunted assemblages. Fossil wood recovered from high-latitude Eocene deposits shows growth rings consistent with seasonally productive forests. Trees of considerable size, growing in soils that were unfrozen year-round. Pollen records from the same regions include taxa associated today with temperate and warm temperate climates, members of the walnut family, the beech family, early relatives of modern conifers, and a range of broad-leaved deciduous species adapted to the long polar day-night cycle that would have characterized these high-latitude environments even in the absence of cold temperatures. The polar forests of the Eocene present an interesting ecological puzzle. At high latitudes, even in the absence of cold temperatures, the seasonal cycle of light and darkness remains governed by the geometry of Earth's orbit. During the polar winter, months of continuous darkness would have imposed a physiological challenge on plant life, regardless of thermal conditions. Evidence suggests that many high-latitude Eocene trees were deciduous, shedding their leaves during the dark season, but grew rapidly and productively during the extended light of the polar summer. This adaptation allowed forests to persist and thrive at latitudes where, today, no trees grow at all. The ecological communities supported by these forests, including insects, early mammals, reptiles, and birds, were correspondingly rich, occupying a thermal niche that has no modern equivalent at those latitudes. Moving toward the mid-latitudes, Eocene terrestrial environments were characterized by broad, humid, heavily vegetated lowlands. In regions corresponding to modern Europe and North America, fossil assemblages indicate the presence of dense subtropical to paratropical forests, environments with closed canopies, high species diversity, and year-round vegetation productivity. These were not tropical rainforests in the strict modern sense, but they occupied a similar ecological role. High biomass, moisture-rich environments supporting diverse communities of plants, invertebrates, and vertebrates. The London clay flora, a well-studied fossil plant assemblage from the early Eocene of southern England, includes evidence of palms, mangroves, and a range of plant genera associated today with tropical and subtropical Asia and the Americas, a direct indicator of the climatic conditions prevailing at what is now a temperate, seasonally cold latitude. Inland continental regions during the Eocene were, in many cases, occupied by shallow lakes, swampy lowlands, and river systems draining into the epicontinental seas that covered large portions of continental interiors. The Green River Formation of the western United States, dating to the Middle Eocene, preserves one of the most detailed records of a warm, ice-free continental interior environment. Deposited in a system of large, shallow lakes surrounded by subtropical woodland, the Green River sediments contain extraordinarily well-preserved fossils of fish, turtles, crocodilians, early horses, palm fronds, and a wide range of invertebrates. The presence of crocodilians, animals that today are restricted to tropical and warm subtropical regions, at what is now a temperate, high-elevation interior, is a direct reflection of the thermal conditions that characterize this landscape during the Eocene. Soil chemistry from the Eocene further corroborates the picture drawn by fossil biology. Paleosols, ancient soils preserved within sedimentary sequences, retain chemical signatures that reflect the temperature and moisture conditions under which they formed. Eocene paleosols from high and mid-latitude sites consistently show evidence of deep weathering, high clay mineral content, warm and chemical profiles associated with warm, humid, pedogenic conditions. In some cases, these profiles resemble those of modern tropical soils, forming under temperatures and rainfall regimes far in excess of what those latitudes experience today. The depth and intensity of Eocene weathering profiles are themselves a form of climatological data. Slow-forming chemical records of sustained warmth accumulated over thousands to tens of thousands of years. Mountainous regions during the Eocene were not absent, but their glacial character was fundamentally different from modern mountain environments. Current evidence does not support the existence of permanent mountain glaciers during the warmest intervals of the Eocene, though some high-altitude and high-latitude peaks may have carried seasonal snow. Without permanent ice and glacial erosion operating at the scales seen in later geological periods, many mountain landscapes would have been more heavily vegetated and chemically weathered than their modern equivalents. River systems draining from Eocene mountain ranges carried large sediment loads derived from intense tropical-style weathering rather than glacial grinding, depositing thick sequences of chemically altered material across adjacent lowland basins. Aridity was not absent from the Eocene world, but its distribution was different. While broad, humid forests dominated much of the mid and high latitudes, evidence from some continental interior regions suggests the existence of seasonally dry environments, areas where rainfall was concentrated in particular seasons, rather than distributed evenly through the year. These seasonal patterns were driven by the same fundamental atmospheric dynamics that produce monsoon climates today, operating within the altered thermal structure of the Eocene atmosphere. However, the overall extent of arid and semi-arid environments appears to have been considerably smaller than in the modern world, where cold ocean currents, rain shadows, and the influence of ice-driven atmospheric circulation contribute to the formation of major desert systems across multiple continents. The terrestrial environments of the Eocene were, in summary, characterized by warmth, humidity, biological productivity, and a latitudinal distribution of vegetation zones shifted dramatically toward the poles relative to today. Forests grew where tundra now exists. Subtropical conditions prevailed where temperate climates now dominate, and the soils were deeply weathered. The river systems were productive, and the biological communities occupying these landscapes were diverse, ecologically complex, and in many cases quite unlike anything that persists in equivalent latitudes today. The physical record they left behind, in rock, in chemistry, in fossil biology, provides a coherent and well-evidenced reconstruction of a terrestrial world operating at a fundamentally different thermal baseline. Of all the systems that distinguish the ice-free Earth from the world that exists today, the oceans were perhaps the most fundamentally transformed, not simply in their extent, though their extent was considerably greater, but in their temperature, their chemistry, their circulation, and the biological communities they supported. The Eocene Ocean was a warmer, more broadly distributed, and in several respects, more biologically productive body of water than its modern counterpart. Understanding it requires examining not just what it contained, but how it functioned as a planetary system. Sea surface temperatures during the Eocene were substantially elevated relative to modern values across all latitudes. Proxy reconstructions derived from the magnesium to calcium ratios in fossil foraminifera, microscopic marine organisms whose shell chemistry records the temperature of the water in which they lived, indicate that tropical sea surface temperatures during the early Eocene may have reached 35 degrees Celsius or higher in some regions. Modern tropical sea surface temperatures average closer to 28 to 29 degrees Celsius. At higher latitudes, the contrast is even more pronounced. Eocene sea surface temperatures in regions corresponding to the modern North Atlantic and Southern Ocean were warm enough to support coral reef systems and other marine communities associated today exclusively with tropical and subtropical waters. The warmth of Eocene surface waters was not uniform, and it was not static. Evidence suggests the existence of warm, shallow epicontinental seas covering large portions of continental interiors, bodies of water that absorbed solar energy efficiently due to their shallow depth and low reflectivity, and that contributed to the regional warming of adjacent land areas. These inland seas also served as important sites of biological productivity and sediment accumulation, and their eventual regression as sea levels fluctuated left behind thick sequences of marine sediment now exposed deep within continental interiors, far from any modern coastline. Ocean circulation during the Eocene was organized around the same fundamental physical principles that govern modern ocean movement: density-driven thermohaline circulation and wind-driven surface currents. But the boundary conditions producing that circulation were substantially different. With no cold polar waters sinking to drive a vigorous deep circulation, and with ocean gateways configured differently by the tectonic positions of the continents, the Eocene Ocean moved differently. The Tethys Sea, still open across the low latitudes, allowed warm surface water to circulate around the globe in a more equatorial band. The Drake Passage between South America and Antarctica had not yet fully opened, meaning that no Antarctic circumpolar current existed to thermally isolate the southern polar region. Warm water could reach high southern latitudes relatively unimpeded, contributing to the absence of Antarctic glaciation. Deep ocean conditions during the Eocene reflect these altered circulation dynamics. Bottom water temperatures, reconstructed from isotopic records in deep-sea sediment cores, were significantly higher than today. Estimates for the early Eocene suggest deep ocean temperatures of 10 to 12 degrees Celsius, compared to the modern average of roughly 2 degrees Celsius. This difference has important consequences for ocean chemistry and biology. Warmer deep water holds less dissolved oxygen, meaning that deep ocean environments during the Eocene may have been more oxygen depleted than today. In some basins, evidence from sediment composition and carbon isotope records suggests the existence of periodically anoxic conditions, intervals during which oxygen levels in the deep water fell low enough to prevent the decomposition of organic material, leading to the accumulation of organic-rich sediments that are today recognized as important source rocks for petroleum deposits. The biological productivity of Eocene surface waters was supported by the broad availability of sunlight across a wider range of latitudes than today, combined with the nutrient cycling sustained by whatever circulation patterns existed in the absence of vigorous thermohaline overturn. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web, diversified significantly during the Eocene. Fossil records of calcareous nanoplankton and dinoflagellates from Eocene marine sediments indicate high species diversity and broad geographic distribution, consistent with warm, productive surface waters extending well beyond the tropics. These primary producers supported diverse communities of zooplankton, early marine vertebrates, and the expanding range of invertebrate life that characterized Eocene marine ecosystems. Carbonate chemistry in the Eocene ocean was also distinct from today. Elevated atmospheric carbon dioxide concentrations, while driving surface warming, also increased the amount of carbon dioxide dissolving into surface seawater, producing carbonic acid and reducing ocean pH. Current evidence suggests that Eocene ocean pH was somewhat lower than pre-industrial modern values, though the buffering capacity of the ocean and the longer timescales over which carbon dioxide rose during the Eocene likely moderated the rate and severity of acidification relative to what is being observed in the modern ocean under rapid anthropogenic emissions. Nevertheless, the carbonate saturation state of Eocene seawater influenced the distribution and preservation of calcifying marine organisms, and its effects are recorded in the depth at which carbonate sediments are preserved in Eocene ocean floor sequences. Coastal environments during the Eocene reflected the combination of high sea levels, warm temperatures, and high biological productivity. Coral reefs, mangrove systems, and shallow carbonate platforms extended to latitudes that today support no such ecosystems. Fossil reef structures from Eocene deposits in what is now northern Europe and the southern United States document the presence of tropical-style carbonate ecosystems at latitudes well outside their modern range. Mangrove pollen and root structures preserved in Eocene coastal sediments from similar latitudes indicate that these highly productive coastal ecosystems, today confined to tropical and warm subtropical shorelines, wrapped around a much larger proportion of the planet's coastline. The Eocene ocean was, in total, a system of greater thermal homogeneity, broader biological reach, and different chemical balance than the ocean of today. Its warmth was sustained by the same elevated greenhouse gas concentrations that warmed the atmosphere and land. Its circulation was shaped by a tectonic configuration that no longer exists. And its biological communities, diverse, productive, and distributed across a wider range of latitudes, laid the ecological foundation for the marine life that would continue to evolve as the planet's climate began its long transition toward cooler conditions. The Eocene ocean was not merely a warmer and more expansive version of the modern sea. It was an ecosystem structured around a different set of ecological dominants, organisms that occupied the upper tiers of the marine food web under conditions of sustained warmth, high productivity, and an absence of the cold water barriers that today define the boundaries of large marine predator ranges. Among the most significant of these dominants were the large marine predators that evolved during and preceding the Eocene, animals whose size, physiology, and ecological roles reflected the particular opportunities and pressures of a warm, productive, ice-free ocean. To understand the predators of the Eocene Sea, it is necessary to first understand the prey base that supported them. Eocene surface waters, as established by fossil and geochemical records, supported diverse and productive communities of fish, early marine mammals, sea turtles, and a wide range of invertebrates. The diversification of bony fish, the teleosts, had proceeded rapidly through the Cretaceous and into the Paleogene, producing by the Eocene a marine fish fauna of considerable ecological complexity. Schools of fish occupying shallow coastal waters, open ocean environments, and reef-associated habitats provided a reliable and abundant food source for large predators operating across multiple ecological zones. It was within this context of biological abundance that the giants of the Eocene Ocean evolved and persisted. Among the most well-documented large predators of the Eocene marine environment are the early sharks. The lineage that would eventually produce Otodus megalodon, the largest shark known from the fossil record, was already established during the Eocene in the form of Otodus obliquus and related species. These were large macropredatory sharks with robust, serrated teeth adapted for seizing and processing large prey. Fossil teeth of Otodus obliques, recovered from Eocene marine deposits across multiple continents, indicate animals reaching estimated lengths of 9 to 10 meters, substantially larger than the modern great white shark, which averages 4 to 5 meters. These animals were not apex predators in isolation. They occupied a marine ecosystem that included other large sharks, early cetaceans, and large bony fish, and their size reflects the ecological productivity and thermal conditions of the Eocene ocean rather than any singular evolutionary anomaly. The early cetaceans, the ancestors of modern whales and dolphins, represent one of the most significant evolutionary transitions recorded in the Eocene fossil record. The first cetaceans evolved from terrestrial artiodactyl ancestors during the early Eocene, returning to the marine environment over a period of millions of years in one of the most thoroughly documented evolutionary transitions in paleontology. Early forms such as Pachycetus, known from the early Eocene of what is now Pakistan, were still largely terrestrial or semi-aquatic, resembling in body plan a large amphibious mammal, rather than anything recognizable as a whale. By the Middle Eocene, however, fully aquatic cetaceans had evolved. Rhodhocetus and related protocetids were capable swimmers with reduced hind limbs and streamlined bodies, occupying a niche somewhere between the amphibious early forms and the fully pelagic whales that would follow. By the late Eocene, the basilosaurids had emerged, a group of fully aquatic cetaceans that represent the first genuinely large marine mammals in the fossil record. Basilosaurus itself, known from well-preserved skeletal material recovered from Eocene deposits in Egypt, the United States, and elsewhere, reached estimated lengths of 15 to 20 meters. Its body was elongated and serpentine relative to modern whales, with small, vestigial hind limbs retained from its terrestrial ancestry, but no longer functional for locomotion. Basilosaurus was a macropredator, equipped with robust, differentiated teeth capable of processing large prey, including fish and other cetaceans. Fossil evidence from the Eocene Tethys region, particularly the remarkably preserved deposits of Wadi al-Hitan in Egypt, a UNESCO World Heritage Site, includes skeletal material of Basilosaurus associated with the remains of smaller cetaceans, providing direct evidence of predatory behavior. The ecological significance of Basilosaurus and related basilosaurids extends beyond their size. They represent the establishment of large marine mammals as significant components of open ocean food webs, a role that, in the modern ocean, is filled by sperm whales, orca, and large baleen whales. In the Eocene, this niche was new. The warm, productive waters of the ice-free ocean provided the energetic foundation necessary to support animals of this scale, and the relative absence of cold water barriers meant that large marine predators could range across broad latitudinal bands without the thermal constraints that today restrict many large marine species to particular ocean zones. Alongside the early sharks and cetaceans, the Eocene ocean supported large marine reptiles in reduced but still ecologically relevant numbers. The age of the great marine reptiles, the ichthyosaurs and plesiosaurs, had ended with the mass extinction at the close of the Cretaceous period, approximately 66 million years ago. However, certain marine reptile lineages persisted into the Eocene. Large sea turtles, some reaching sizes considerably greater than any modern species, occupied coastal and open ocean environments. Early members of the mosasaur lineage had not survived the end Cretaceous extinction, but the ecological space they had occupied was being progressively filled by the diversifying cetaceans and sharks of the Eocene ocean. The distribution of these large marine predators across Eocene ocean basins reflects the thermal and ecological conditions of the period. Fossil material of large Eocene sharks and early cetaceans has been recovered from deposits spanning the former Tethys Sea, the early Atlantic, the Indo-Pacific region, and the shallow epicontinental seas of North America and Europe. This broad distribution indicates that the warm, productive conditions of the Eocene ocean were not confined to a narrow tropical band, but extended across a wide range of latitudes, providing the ecological substrate necessary for large predators to persist and diversify across geographically separated ocean basins. What the fossil record of Eocene marine predators ultimately documents is an ocean in which size, as an ecological strategy, was supported by the particular conditions of a warm, productive, ice-free world. The energetic resources available in a broadly warm ocean, distributed across a wider range of latitudes than today, allowed predators of considerable scale to evolve, persist, and diversify. The giants of the Eocene Sea were not anomalies. They were the predictable products of an ocean operating at a higher thermal and biological baseline than the one that exists in the present. The Eocene was not only a period of familiar animals growing larger or ranging more widely than their modern counterparts. It was also a period of genuine biological novelty, a time when evolution was actively exploring morphological and ecological territory that has since been largely abandoned. The warm, stable, productive environments of the ice-free world provided conditions under which unusual body plans, unconventional ecological strategies, and transitional forms could persist long enough to leave a record. Many of the organisms documented from Eocene fossil sites bear only a distant resemblance to anything living today. They are not simply older versions of modern animals. They are, in several cases, evolutionary experiments that ran their course within the Eocene and left no direct descendants in the modern fauna. Understanding why the Eocene produced such biological diversity requires appreciating the ecological context into which these organisms were born. The end Cretaceous mass extinction, approximately 66 million years ago, had eliminated a substantial proportion of Earth's species, including all non-avian dinosaurs, the large marine reptiles, many lineages of marine invertebrates, and a broad range of terrestrial and aquatic vertebrates. The ecological vacancies left by this extinction were enormous. The Paleocene and Eocene that followed were periods of rapid ecological diversification, intervals during which surviving lineages expanded into unoccupied niches, evolved new body plans, and established ecological relationships with no direct Mesozoic precedent. The warm, resource-rich environments of the Eocene accelerated this process, providing the energetic and spatial conditions necessary for biological experimentation at a broad scale. Among the most striking of the Eocene's unfamiliar organisms were the early ungulates, hoofed mammals, whose Eocene representatives bore little resemblance to the horses, deer, cattle, and rhinoceroses that descended from them. The condylarths, a broadly defined and likely paraphyletic grouping of early placental mammals, occupied a wide range of body sizes and ecological roles during the early Paleogene. Some were small, generalist omnivores. Others were larger, with teeth suggesting browsing or frugivorous diets. Their limb proportions, dental morphology, and inferred locomotor styles were often intermediate, combining features that, in modern mammals, are associated with quite different ecological roles. They were, in the strict sense, transitional forms, animals occupying ecological space between the generalized small mammals of the Cretaceous and the specialized large herbivores that would come to dominate later Cenozoic landscapes. The perissodactyls, the lineage that includes modern horses, tapirs, and rhinoceroses, first appeared during the early Eocene, and their earliest representatives were remarkably unlike their modern descendants. Eohippus, more formally known as Hyracotherium, is one of the most frequently cited examples of an Eocene mammal whose morphology diverges substantially from modern expectations. This early horse relative was small, comparable in size to a medium dog, with 4 toes on its front feet and 3 on its rear, padded feet rather than hooves, and teeth adapted for browsing soft vegetation rather than grazing grasses. It inhabited the dense, humid forests of the early Eocene, occupying an ecological niche quite different from the open grassland environments associated with modern horses. The trajectory from Hyracotherium to Equus, the modern horse, spans tens of millions of years and involves a gradual increase in body size, reduction in toe number, and shift in dental morphology, tracking the spread of grasslands across the continents. In the Eocene, that trajectory had barely begun. Marine environments of the Eocene contained their own roster of biologically unfamiliar organisms. Among the most significant were the archaeocetes, the early cetaceans discussed in the context of marine predators, whose transitional morphology between terrestrial and fully aquatic life represents one of the most visually striking evolutionary sequences in the fossil record. But beyond the archaeocetes, Eocene seas supported a range of other unusual marine vertebrates. The early Sirenians, the lineage that includes modern manatees and dugongs, were undergoing their own transition from terrestrial to aquatic life during the Eocene. Early forms, such as Pesosiren, known from Middle Eocene deposits in Jamaica, retained 4 functional limbs and were likely capable of both terrestrial locomotion and swimming, occupying a transitional ecological position analogous to that of the early cetaceans, but following an independent evolutionary trajectory. Among marine invertebrates, the Eocene saw the diversification of several groups whose Eocene representatives were morphologically distinct from their modern counterparts, or have since gone entirely extinct. The nummulidids, large coin-shaped foraminifera, reached sizes during the Eocene that are extraordinary for single-celled organisms, with some species producing tests several centimeters in diameter. These organisms were so abundant in shallow Eocene marine environments that their accumulated shells form thick limestone deposits across the former Tethys region, including the stone from which the Egyptian pyramids were constructed. The ecological success of nummulidids in the warm and shallow Eocene seas reflects conditions of carbonate saturation and thermal stability that favored their particular biology, conditions that have not recurred at comparable scale in the time since. Terrestrial arthropods of the Eocene are known in exceptional detail from amber deposits, fossilized tree resin that preserves organisms with microscopic fidelity. Eocene amber from deposits in the Baltic region, Myanmar, and elsewhere contains a rich record of insects, spiders, mites, and other small invertebrates, many of which belong to lineages that are either extinct or have no close modern equivalent in the regions where the amber formed. The composition of these amber faunas reflects the warm, forested environments in which the resin-producing trees grew, and the preserved organisms document ecological interactions, parasitism, predation, mutualism, that provide a detailed window into the functioning of Eocene forest ecosystems at a scale of biological resolution rarely achievable in the fossil record. Among birds, the Eocene was a period of significant diversification following the extinction of non-avian dinosaurs. Many Eocene bird lineages were experimentally large. Gastornis, a large flightless bird known from Eocene deposits in Europe and North America, stood approximately 1.75 meters tall and possessed a massive, deep beak whose function has been debated. Early interpretations suggested a predatory role, but more recent isotopic analysis of Gastornis bone material indicates a diet more consistent with hard plant material such as seeds and nuts, suggesting that this large and robust bird occupied a herbivorous or omnivorous niche rather than a carnivorous one. Regardless of its precise diet, Gastornis represents a body plan, a large, flightless, heavily built bird that has no modern equivalent in the environments where it lived. The early primates of the Eocene occupy a particular scientific interest given their relevance to human evolutionary history. The first definitively identified primates appear in the fossil record during the Paleocene and early Eocene, and by the Middle Eocene, multiple primate lineages had diversified across the warm forests of North America, Europe, Asia, and Africa. These early primates, the adipids and omomiids, were small, arboreal, and in many respects quite different from the anthropoid primates that would later give rise to monkeys, apes, and eventually humans. Their morphology, inferred behavior, and ecological roles within Eocene forest communities represent the earliest chapters of a lineage whose later history would unfold across the cooling climates of the Oligocene, Miocene, and Pliocene. What the biological record of the Eocene ultimately demonstrates is a world in which the boundaries of viable morphology and ecological strategy were being actively tested. The warm, stable, resource-rich environments of the ice-free Earth provided the conditions under which novel body plans could persist. Transitional forms could survive long enough to give rise to descendant lineages, and ecological roles left vacant by the end. Cretaceous extinction could be progressively filled by organisms whose designs were, by any modern standard, genuinely unfamiliar. The story of life moving from water onto land is not a single event. It is not a moment of transition that can be pinned to a particular geological horizon or attributed to a single lineage making a decisive crossing from one medium to another. It is, instead, a prolonged and complex process, one that unfolded across hundreds of millions of years, involved multiple independent lineages, and produced a range of intermediate forms whose biology straddled the boundary between aquatic and terrestrial existence in ways that have no precise modern equivalent. The Eocene represents not the beginning of this process, but one of its most ecologically significant chapters, a period during which the warm, productive terrestrial environments of the ice-free world supported the diversification and expansion of land-dwelling vertebrate life at a scale and complexity not previously achieved. To understand the state of terrestrial vertebrate life during the Eocene, it is necessary to briefly trace the earlier stages of the water-to-land transition. The first vertebrates to make sustained use of terrestrial environments were the tetrapods, four-limbed vertebrates that evolved from lobe-finned fish during the late Devonian period, approximately 375 million years ago. These early tetrapods, represented by animals such as Tiktaalik and Acanthostega, and were aquatic or semi-aquatic organisms whose limbs were capable of supporting their weight in shallow water or on temporarily exposed mudflats, but whose physiology remained closely tied to aquatic environments. They breathed through both lungs and gills, laid eggs in water, and almost certainly returned to aquatic environments for reproduction and thermoregulation. The progressive colonization of terrestrial environments by vertebrates over the following hundreds of millions of years involved a series of biological innovations that reduced dependence on standing water. The evolution of the amniota egg, a shelled, internally moistened egg that could be laid on dry land without desiccating, was one of the most significant of these innovations, allowing reptiles and their descendants to reproduce entirely away from water. The development of dry, scale-covered or keratinized skin reduced water loss through the body surface. The refinement of limb musculature and skeletal structure allowed sustained terrestrial locomotion across a range of substrates. By the time of the Permian and Triassic periods, terrestrial vertebrates had diversified extensively, occupying a broad range of ecological roles across the land surfaces of the supercontinent Pangaea. The end Cretaceous mass extinction reset much of this terrestrial diversity. The elimination of non-avian dinosaurs, which had dominated terrestrial ecosystems for over 150 million years, created an ecological landscape in which the surviving mammals, birds, reptiles, and amphibians faced reduced competition for resources and space. The Paleocene and Eocene that followed were periods of rapid mammalian diversification as surviving lineages expanded into the ecological roles vacated by the dinosaurs. The warm, forested environments of the Eocene provided the thermal and nutritional conditions under which this diversification proceeded at an accelerated rate. Amphibians, the most direct living representatives of the original water-to-land transition, occupied a distinct and ecologically important position in Eocene terrestrial ecosystems. Modern amphibians, including frogs, salamanders, and caecilians, retain a fundamental dependence on moist environments for reproduction, as their eggs lack the protective membranes of amniote eggs and must be laid in or near water. This reproductive constraint limits amphibian distribution to environments with reliable moisture availability. In the warm, humid Eocene world, with its broadly distributed rainfall and extensive riparian and wetland environments, the conditions suitable for amphibian life extended across a much wider geographic range than today. Fossil frog material from Eocene deposits at high latitudes documents the presence of anurans in environments that today are far too cold and dry to support them. The reptiles of the Eocene terrestrial world were diverse and, in several lineages, considerably larger than their modern counterparts. Crocodilians, as noted in the context of Eocene continental interiors, occupied a much broader latitudinal range during the Eocene than they do today, but their distribution reflecting the absence of the cold winters that now restrict them to tropical and warm subtropical regions. Beyond crocodilians, Eocene terrestrial reptile faunas included large snakes, among them Titanoboa kerejonensis, known from slightly earlier Paleocene deposits in Colombia, but representing a body plan and ecological role consistent with the warm Paleogene world. Titanoboa reached estimated lengths of 12 to 15 meters and body masses, suggesting it was the largest snake known from the fossil record. Its size is directly relevant to the thermal conditions of the time. Snake metabolism and maximum body size are constrained by ambient temperature, as these ectothermic animals depend on environmental heat for physiological function. The existence of Titanoboa is therefore itself a form of paleoclimatic evidence, a biological indicator of the sustained warmth that characterized the low-latitude terrestrial environments of the early Paleogene. Early mammals diversifying across Eocene land surfaces occupied an extraordinarily wide range of body sizes and ecological roles compared to their Cretaceous predecessors, which had been largely small, nocturnal, and insectivorous. By the Eocene, mammals had expanded into herbivory, carnivory, omnivory, and a range of locomotor specializations, including cursorial, arboreal, fossorial, and semi-aquatic lifestyles. The forests and wetlands of the Eocene provided both the structural diversity of habitat and the biological productivity necessary to support this ecological radiation. Tall, enclosed canopy forests offered arboreal niches for climbing mammals. Dense understory vegetation supported browsers and frugivores. Riparian corridors and lake margins provided habitat for semi-aquatic species. The mosaic of Eocene terrestrial environments, shaped by the thermal and hydrological conditions of the ice-free world, directly enabled the ecological diversification of early mammals. The ecological interactions structuring Eocene terrestrial communities, predation, herbivory, competition, mutualism, were in many respects analogous in their functional logic to those operating in modern ecosystems, even where the specific organisms involved were quite different. Large herbivores consumed vegetation, influencing plant community composition and structure. Predators regulated herbivore populations and behavior, and decomposers and invertebrates cycled nutrients through soils and leaf litter. These functional relationships, operating within the particular biological and physical context of the warm Eocene world, produced terrestrial ecosystems of considerable ecological complexity. Systems whose diversity and productivity were directly sustained by the thermal and hydrological conditions of a planet without permanent ice. The ecological diversification of terrestrial vertebrates during the Eocene was not simply a matter of filling vacant niches with smaller or generalized forms. It was, in several lineages, a process of progressive size increase, a trajectory toward larger body masses that was directly enabled by the warm, productive, and broadly forested environments of the ice-free world. The relationship between body size and environmental conditions is not incidental. It is governed by well-established ecological and physiological principles that connect the thermal baseline of an environment, the productivity of its vegetation, and the digestive and metabolic requirements of large herbivores in ways that make the Eocene's warm, resource-rich landscapes a predictable setting for the evolution of massive terrestrial animals. The ecological principle most directly relevant here is the relationship between primary productivity and the maximum body size sustainable within a given ecosystem. Large herbivores require large quantities of plant material to meet their energetic needs. The amount of plant material available in a given environment is a function of photosynthetic productivity, which is in turn a function of temperature, water availability, sunlight, and nutrient supply. The warm, humid, broadly forested environments of the Eocene supported substantially higher primary productivity across a wider range of latitudes than the modern world. More vegetation, more widely distributed, meant that the energetic foundation capable of supporting large herbivores extended across a much greater geographic area than it does today. And this created the ecological conditions under which large body size was not merely possible, but, for certain lineages, advantageous. Among the most striking examples of Eocene large-bodied terrestrial herbivores are the Brontotheres, a lineage of perissodactyls, distantly related to modern rhinoceroses and horses, that evolved rapidly during the Eocene and reached considerable body sizes by the Middle and Late Eocene. Early Brontotheres from the beginning of the Eocene were relatively modest in size, comparable to a large dog. By the Late Eocene, however, Brontotheres such as Megacerops had grown to the size of modern rhinoceroses or larger, with some estimates suggesting body masses in excess of 1 to 2 tons. Their skulls bore prominent bony protuberances, whose function remains debated. Possibilities include intraspecific combat and display or thermoregulation, but whose scale reflects the substantial increase in overall body mass achieved within this lineage over a relatively short geological interval. Brontotheres were browsers, likely feeding on the soft leaves and fruit of the dense Eocene forests, and their distribution across North America and Asia reflects the geographic extent of the warm forested environments that supported their particular dietary requirements. The Uintatheres represent another lineage of large Eocene herbivores, whose body plan has no close modern equivalent. These were massive, heavily built animals, among the largest land mammals of the Eocene, with skulls bearing multiple pairs of bony knobs and, in males, elongated canine teeth. Uintatheres, such as Uintatherium, reached body masses estimated at several tons, occupying an ecological role broadly analogous to that of modern large herbivores such as hippopotamuses or rhinoceroses, though their precise dietary preferences and habitat associations are inferred primarily from dental morphology and depositional context rather than direct behavioral evidence. The co-occurrence of Uintatheres with other large herbivores in Eocene fossil assemblages from North America suggests that the productivity of Eocene terrestrial environments was sufficient to support multiple large-bodied herbivore species within the same ecological community, a level of megafaunal diversity that requires substantial and reliable plant biomass to sustain. In Asia, and the Eocene and continuing into the Oligocene saw the evolution of the Paraceratheres, a lineage of hornless rhinoceroses that would eventually produce the largest land mammals known from the fossil record. While the largest Paraceratheres, including Paraceratherium itself, are more fully represented in Oligocene deposits, the lineage's roots extend into the Eocene, and the ecological conditions that enabled their eventual scale were established during the warm Eocene world. Paraceratherium reached estimated shoulder heights of approximately 4.5 to 5 meters and body masses of 15 to 20 tons, feeding on the leaves of tall trees across the broad, warm landscapes of Central and Eastern Asia. The existence of an animal of this scale is itself a reflection of the environmental productivity and thermal conditions that characterize the Paleogene world, conditions that made available, across vast geographic areas, the quantity of high-quality plant material necessary to sustain a browsing herbivore of extraordinary dimensions. The evolution of large body size in Eocene herbivores was not driven by a single selective pressure. Multiple factors likely contributed, operating simultaneously across different lineages and environments. Larger body size confers advantages in thermoregulation. Larger animals have a lower surface area to volume ratio, which reduces heat loss in cooler conditions and, in the warm Eocene, may have assisted in managing the heat load of a high-temperature environment through thermal inertia. Larger digestive systems allow more efficient processing of low-quality plant material, extending the range of vegetation types that can be exploited as food sources. Larger body size also provides a degree of protection against predation, reducing vulnerability to all but the largest and most capable predators. In the context of the Eocene, where predator diversity was also increasing, the selective advantages of large size were likely operating across multiple dimensions simultaneously. The predators sharing Eocene terrestrial environments with these large herbivores were themselves undergoing size increases and ecological specialization, responding to the availability of large prey. The Mesonychids, a group of carnivorous mammals whose systematic relationships have been revised multiple times in the paleontological literature, included large-bodied predators during the Paleocene and early Eocene, though their diversity declined as other carnivore lineages expanded. The creodonts, an extinct order of carnivorous mammals, were among the dominant large predators of the Eocene, with forms such as Sarcastodon from the late Eocene of Mongolia reaching estimated body masses comparable to a large bear. These animals occupied the ecological role of apex terrestrial predator across much of the Eocene world, hunting or scavenging the large herbivores that shared their environments. The size and diversity of both herbivores and predators in Eocene terrestrial ecosystems reflects a fundamental ecological truth. The scale of life sustainable within any environment is ultimately constrained by the productivity of that environment's primary producers. The warm, humid, broadly forested landscapes of the ice-free Eocene world were among the most productive terrestrial environments in the history of the planet, supporting a biomass of plant life sufficient to sustain animal communities of considerable scale and diversity. The massive land animals of the Eocene were not evolutionary accidents. They were the predictable products of an ecosystem operating at a higher energetic baseline than the one that supports terrestrial megafauna today. In a world where the thermal and hydrological conditions enabling high plant productivity extended from the tropics to within a relatively short distance of the poles themselves. The ecological architecture of any terrestrial ecosystem is shaped, in significant part, by its apex predators. These are the organisms occupying the highest trophic positions, animals whose predatory activity regulates the population dynamics of herbivores, influences the structure of plant communities through cascading ecological effects, and maintains the functional balance of the broader ecosystem. In the warm, productive terrestrial environments of the Eocene, apex predators were diverse, ecologically significant, and in several lineages, morphologically unlike anything that occupies equivalent ecological roles in the modern world. Understanding them requires examining not only their biology, but the ecological context that produced them. A landscape of high herbivore diversity and abundance, extensive forested habitat, and thermal conditions that supported large-bodied ectotherms and endotherms alike. The dominant large predators of Eocene terrestrial ecosystems were not the felids and canids that dominate modern carnivore guilds. Those lineages were either absent or represented only by small, generalized early forms during the Eocene. Instead, the apex predator roles were occupied by groups that have since declined or gone entirely extinct. The creodonts, the mesonychids, and certain large reptilian predators whose ranges extended into mid and high latitudes under the thermal conditions of the ice-free world. Each of these groups approached the ecological problem of large prey capture through different morphological solutions, and their coexistence within Eocene ecosystems reflects the diversity of predatory strategies that the period's ecological conditions could sustain. The creodonts were among the most ecologically significant of the Eocene's large terrestrial predators. This extinct order of carnivorous mammals diversified extensively during the Paleocene and Eocene, producing a range of body sizes and morphological types adapted to different predatory roles. The hyenodontids, one of the two major creodont families, persisted from the Eocene well into the Miocene and included some of the largest terrestrial mammalian predators of the Paleogene. Hyenodon itself, known from multiple species of varying size, was a cursorial predator with a large skull, powerful jaws, and shearing carnassial teeth adapted for processing flesh and bone. Larger hyenodontid species from the late Eocene and Oligocene reached body masses comparable to a modern lion or larger, occupying the role of dominant pursuit predator across the open and semi-open environments of their range. Their hunting strategy, inferred from limb proportions and dental morphology, appears to have emphasized active pursuit and powerful bite force rather than the ambush tactics associated with modern large felids. The Oxyaenids, the second major creodont family, were generally more robust and shorter-limbed than the hyenodontids, suggesting ecological roles more consistent with ambush predation or the processing of large carcasses than sustained pursuit. Oxyaena and related genera from the early Eocene were medium to large-bodied, with heavily muscled forelimbs and broad, powerful skulls. Their morphology has been compared, in functional terms, to that of modern wolverines or large mustelids, though their body masses and ecological significance within Eocene predator guilds substantially exceeded those of any living mustelid. The coexistence of Oxyaenids and hyenodontids within early Eocene ecosystems suggests a degree of niche partitioning within the large predator guild, different body plans and hunting strategies reducing direct competition between contemporaneous carnivore lineages. Among the most ecologically unusual predators of the Eocene terrestrial world were the large flightless birds that occupied carnivorous or omnivorous roles across several continents. Gastornis, discussed previously in the context of biological novelty, and has been reinterpreted in recent analyses as more likely herbivorous or omnivorous than strictly predatory. However, other large flightless birds of the Eocene and early Oligocene present a clearer case for apex predatory roles. The Forus racids, commonly known as terror birds, were large, flightless, cursorial predators whose fossil record extends from the Eocene of South America across subsequent geological periods. Early Forus racids from Eocene deposits were already substantially built, with large hooked beaks adapted for delivering powerful strikes to prey, and long, powerful legs suited to rapid terrestrial locomotion. South America during the Eocene was an island continent, isolated from North America, and its predator guild was consequently structured differently from contemporaneous ecosystems elsewhere. In the absence of large mammalian carnivores occupying the apex predator role, Forus racids filled this ecological position with considerable success, a pattern of avian apex predation with no modern terrestrial equivalent. Large reptilian predators extended their ranges significantly under the thermal conditions of the Eocene. Crocodilians, whose modern distribution is restricted by their ectothermic physiology to tropical and warm subtropical environments, occupied mid- and high-latitude terrestrial and riparian environments during the Eocene that are today inaccessible to them. Large crocodilian species from Eocene deposits in North America and Europe document the presence of these animals at latitudes where winter temperatures today would preclude their survival. The ecological role of large crocodilians in Eocene ecosystems extended beyond purely aquatic predation. These animals were capable of terrestrial movement and likely ambushed prey at the margins of the rivers, lakes, and wetlands that were broadly distributed across the warm Eocene landscape. The interactions between Eocene apex predators and the large herbivore communities they preyed upon were structured by the same ecological principles governing predator-prey dynamics in any ecosystem: pursuit and evasion, predator detection, herd behavior, and the energetic calculus of predation attempts relative to the calories obtained from successful kills. Large herbivores, such as Brontotheres and Uintatheres, with their substantial body masses and, in some cases, defensive morphological features, they would have represented high reward but high risk prey for even the largest Eocene predators. Smaller and more vulnerable herbivores, the early horses, primitive artiodactyls, and medium-sized browsers occupying the middle trophic levels of Eocene ecosystems, likely formed the primary dietary base for most large predators, with attacks on megafaunal herbivores representing opportunistic rather than routine predation. The ecological balance maintained by Eocene predator guilds was itself a product of the environmental conditions sustaining it. High herbivore diversity and abundance, supported by the productivity of warm Eocene vegetation, provided the prey base necessary to sustain diverse and large-bodied predator communities. The broad geographic extent of suitable habitat, uninterrupted by the cold barriers that today fragment terrestrial ecosystems across mid and high latitudes, allowed predator populations to maintain the geographic ranges and population sizes necessary for long-term ecological viability. The predators of the ice-free world were not simply larger or stranger versions of modern carnivores. They were the functional products of an ecosystem structured around different thermal, vegetational, and ecological parameters. A predator guild shaped by and dependent upon the particular conditions of a planet that has not existed for approximately 34 million years. For tens of millions of years, the warm, ice-free conditions of the Eocene had persisted with sufficient stability to support the diverse and productive ecosystems described across the preceding chapters. The forests extended to high latitudes. The oceans were warm and broadly distributed. The predator and herbivore communities of the terrestrial world were structured around a thermal and ecological baseline that had remained broadly consistent across geological timescales. But stability, in the context of Earth's climate system, is never absolute. Beneath the apparent constancy of the Eocene world, a set of slow, interconnected processes was accumulating. Processes that would, over millions of years, shift the planet's energy balance away from the warm greenhouse state and toward the cooler conditions that would eventually produce permanent polar ice. The signals of this impending transition are recorded in the geological and geochemical record with a clarity that only becomes apparent when examined across the full temporal span of the Eocene. Individual snapshots of Eocene geology can appear broadly uniform: warm temperatures, high sea levels, productive ecosystems. But when proxy records of temperature, carbon dioxide concentration, and ocean chemistry are assembled into continuous time series spanning the full duration of the epoch, a directional trend becomes visible. Global mean temperatures, while fluctuating on shorter timescales, show a general declining trajectory across the Eocene. Deep ocean temperatures, recorded in the oxygen isotope compositions of benthic foraminifera from sediment cores drilled across multiple ocean basins, decreased progressively from the early Eocene climatic optimum toward the end of the epoch. This cooling was not linear or uninterrupted. It included intervals of relative warmth and transient thermal events, but its overall direction was consistent and measurable. One of the most significant of these transient events was the Middle Eocene climatic optimum, a period of renewed warmth occurring approximately 40 million years ago that temporarily reversed the general cooling trend. Proxy records indicate a pulse of elevated temperatures and, in some records, elevated carbon dioxide concentrations during this interval, followed by a return to the cooling trajectory. The existence of this transient warm interval within a broader cooling trend illustrates the complexity of Eocene climate dynamics, a system not simply moving in one direction, but responding to multiple forcing factors operating across different timescales, producing a pattern of variability superimposed on a longer-term directional change. The atmospheric carbon dioxide record across the Eocene is central to understanding this cooling trajectory. Elevated carbon dioxide concentrations were the primary driver of the greenhouse warmth characterizing the early Eocene, and their progressive decline through the epoch correspondingly reduced the greenhouse forcing sustaining that warmth. The causes of this carbon dioxide decline are multiple and interconnected. Enhanced weathering of silicate rocks, a process in which atmospheric carbon dioxide reacts with exposed rock surfaces, drawing carbon out of the atmosphere and eventually depositing it as carbonate sediments in the ocean. Accelerated during intervals of tectonic activity that exposed large areas of fresh rock to weathering. The continued movement of tectonic plates altered the configuration of ocean basins and continental margins, influencing the patterns of upwelling and carbon burial that regulate atmospheric carbon dioxide on geological timescales. The collision of the Indian subcontinent with Asia, which had begun during the early Eocene and would continue to build the Himalayan mountain range across subsequent millions of years, and is considered a significant driver of enhanced silicate weathering and long-term carbon dioxide drawdown during the Paleogene. Tectonic changes were also altering the configuration of ocean gateways in ways that would have profound consequences for global heat distribution. The gradual closure of the Tethys Sea, driven by the northward movement of the African and Indian plates toward Eurasia, was progressively restricting the low-latitude oceanic corridor through which warm tropical water had circulated around the globe. As this gateway narrowed and eventually closed, the pattern of global ocean heat transport changed, reducing the efficiency with which warm equatorial water reached high latitudes and contributing to the progressive cooling of polar regions. Simultaneously, the Southern Ocean geometry was approaching the configuration that would eventually allow the formation of the Antarctic circumpolar current, though the Drake Passage between South America and Antarctica had not yet fully opened during the Eocene itself. Within the biological record, there are indications that Eocene ecosystems were beginning to respond to the subtle shifts in climate occurring during the later part of the epoch. Palynological records, the fossil pollen sequences preserved in lake sediments and peat deposits from high-latitude sites, show a gradual shift in vegetation composition during the Middle and Late Eocene, with some cold-sensitive taxa becoming less abundant and more temperate-adapted species increasing in relative proportion. These changes were not abrupt or catastrophic during the Eocene itself, but they represent the earliest biological signals of the cooling that would accelerate dramatically at the Eocene-Oligocene boundary. The forests of the high latitudes did not disappear overnight. They changed incrementally, tracking the slow shift in thermal conditions with the generational timescales of plant community turnover. Ocean biology similarly records the approaching transition. The composition of planktonic microfossil assemblages in late Eocene marine sediments shows shifts consistent with cooling surface waters, particularly at higher latitudes. Warm water foraminifera species decline in relative abundance in late Eocene samples from mid and high latitude sites, replaced progressively by forms tolerant of cooler conditions. These microfossil assemblages are sensitive recorders of sea surface temperature change, and their compositional shifts across the late Eocene provide a high-resolution record of the ocean's response to the declining greenhouse forcing of the period. The late Eocene also saw several large bolide impacts whose climatic and biological consequences have been investigated in the geological record. the Chesapeake Bay impact structure, and the Popigai crater in Siberia, both dating to approximately 35 million years ago near the end of the Eocene, represent significant impact events whose short-term climatic effects, injection of dust and aerosols into the atmosphere, transient cooling, disruption of photosynthesis, would have been superimposed on the longer-term cooling trend already underway. The precise contribution of these impacts to the acceleration of Eocene cooling and the subsequent glaciation of Antarctica remains a subject of active scientific investigation, but their occurrence in the geological record near the Eocene-Oligocene boundary has made them a persistent focus of research into the causes of this major climatic transition. What the late Eocene record documents, across its multiple proxy archives, is a world in which the conditions sustaining warmth were being progressively eroded by the slow operation of geological and atmospheric processes. The ice-free state that had characterized Earth for tens of millions of years was not collapsing suddenly. It was being gradually undermined by declining carbon dioxide, by changing ocean gateways, by shifting tectonic configurations, in a process whose full consequences would only become apparent as the planet crossed the thermal threshold beyond which permanent ice could begin to accumulate. The transition from the warm, ice-free conditions of the Eocene to the glaciated world that followed was one of the most consequential climatic shifts in the history of complex life on Earth. It was not an instantaneous event. It was the culmination of a long, multi-causal process whose individual components had been operating across millions of years, each contributing incrementally to a shift in the planet's energy balance that eventually crossed a threshold from which there was no immediate return. The moment that threshold was crossed, the point at which permanent ice began to accumulate on Antarctica for the first time in tens of millions of years, is recorded in the geological record with remarkable clarity, marking what scientists refer to as the Eocene-Oligocene transition, or EOT, approximately 34 million years ago. And the oxygen isotope record preserved in the shells of benthic foraminifera from deep-sea sediment cores provides the most continuous and globally coherent record of this transition. Oxygen exists in two stable isotopic forms, oxygen-16 and oxygen-18, whose relative proportions in seawater change as ice accumulates on land. When water evaporates from the ocean and falls as snow, it preferentially incorporates the lighter oxygen-16 isotope. As this water is locked into growing ice sheets rather than returning to the ocean, the remaining seawater becomes progressively enriched in oxygen-18. Organisms building their shells from seawater record this isotopic shift, and the shells they leave behind in marine sediments preserve it across geological time. At the Eocene-Oligocene boundary, sediment cores from ocean basins worldwide show a sharp and substantial increase in oxygen-18 values, a signal interpreted as reflecting both the cooling of deep ocean waters and the rapid accumulation of ice on Antarctica. This isotopic shift, known as the EOT isotope excursion, is one of the most distinctive features in the Cenozoic paleoclimate record. The causes of this transition are understood through a convergence of geological, geochemical, and modeling evidence, and they involve several interacting mechanisms operating across different timescales. The long-term decline in atmospheric carbon dioxide concentrations across the Eocene, driven by enhanced silicate weathering and changes in organic carbon burial, had progressively reduced the greenhouse forcing maintaining global warmth. By the late Eocene, and carbon dioxide concentrations had fallen to levels at which climate models indicate the Antarctic ice sheet could begin to nucleate, to form and sustain itself against the seasonal warming that would otherwise melt seasonal snowfall. Proxy reconstructions of atmospheric carbon dioxide across the Eocene-Oligocene boundary, derived from the boron isotope compositions of marine carbonates and the carbon isotope signatures of ancient soils, consistently indicate a decline in carbon dioxide concentrations coinciding with the onset of Antarctic glaciation, supporting the interpretation that greenhouse gas drawdown was a primary driver of the transition. Tectonic reorganization of ocean gateways played a complementary and closely debated role in the cooling transition. The opening of the Drake Passage between the southern tip of South America and the Antarctic Peninsula, allowing the establishment of the Antarctic circumpolar current, has long been considered a key factor in the thermal isolation of Antarctica. By permitting a continuous eastward-flowing current to encircle Antarctica without interruption by continental landmasses, the Antarctic circumpolar current effectively reduced the transport of warm subtropical water to high southern latitudes, allowing Antarctica to cool progressively and accumulate ice. The precise timing of the Drake Passage opening relative to the onset of Antarctic glaciation has been a subject of ongoing scientific debate, with some studies placing its initial opening earlier in the Eocene and others suggesting it was not fully developed until after glaciation had already begun. Current evidence suggests that the opening of the Drake Passage contributed to the conditions favoring glaciation, but was likely not sufficient on its own, operating in conjunction with the declining carbon dioxide trend rather than as a singular cause. The Tasman Gateway, the oceanic passage between Australia and Antarctica, also widened progressively during the Eocene as Australia moved northward away from Antarctica. This widening similarly contributed to the developing circumpolar circulation pattern and the thermal isolation of the Antarctic continent. The combined effect of these two gateway changes, operating across the same broad interval as the carbon dioxide decline, produced a convergence of forcing factors that collectively pushed the climate system toward the glaciation threshold. The ice sheet that formed on Antarctica at the Eocene-Oligocene boundary was not a gradual, incremental accumulation. Evidence from sediment cores and ice-rafted debris records suggests that the initial glaciation of Antarctica may have proceeded relatively rapidly in geological terms, over perhaps 100,000 years or less, once the threshold conditions were met. This rapidity reflects the operation of positive feedbacks within the climate system. As ice began to accumulate, its high reflectivity reduced the amount of solar energy absorbed by the Antarctic surface, cooling the region further and allowing more ice to form. This ice albedo feedback, operating in the opposite direction from the warming feedback that had helped maintain the ice-free Eocene climate, accelerated the transition once it began. The consequences of Antarctic glaciation extended well beyond the southern polar region. The formation of a large ice sheet on Antarctica locked up substantial quantities of water that had previously been in the ocean, lowering global sea levels. Estimates of sea level fall associated with the initial Eocene-Oligocene glaciation range from approximately 30 to 70 meters, reflecting the uncertainty in reconstructing the volume of the early Antarctic ice sheet. This sea level drop exposed previously submerged continental shelves, altered coastal configurations, and drained the shallow epicontinental seas that had covered large portions of continental interiors during the warm Eocene. Terrestrial environments that had been marine were returned to land, reshaping the geographic distribution of habitats available to terrestrial organisms. Ocean circulation was profoundly reorganized by the developing Antarctic ice sheet and the associated cooling of southern ocean waters. The formation of cold, dense bottom water around Antarctica, Antarctic bottom water, established a new mode of deep ocean circulation driven by the sinking of cold polar water, replacing the more sluggish, thermally homogeneous deep circulation of the warm Eocene ocean. This reorganization increased the ventilation of the deep ocean, raising oxygen levels in deep water environments and altering the chemistry and biology of the ocean floor across the globe. The modern pattern of thermohaline circulation, in which cold water sinks at high latitudes and spreads along the ocean floor, has its origins in this Eocene-Oligocene reorganization of the deep ocean. The atmospheric consequences of the cooling transition included a strengthening of the meridional temperature gradient, the difference in temperature between the equator and the poles, as polar regions cooled relative to the tropics. This strengthened gradient intensified atmospheric circulation, producing stronger and more defined jet streams, more pronounced seasonal temperature contrasts at mid-latitudes, and a reorganization of global precipitation patterns. Environments that had been broadly humid during the Eocene began to experience more pronounced seasonality, and the latitudinal boundaries of vegetation zones shifted progressively toward the equator as the thermal conditions supporting high-latitude forests declined. The transition from the warm, ice-free conditions of the Eocene to the glaciated world that followed was one of the most consequential climatic shifts in the history of complex life on Earth. It was not an instantaneous event. It was the culmination of a long, multi-causal process whose individual components had been operating across millions of years, each contributing incrementally to a shift in the planet's energy balance that eventually crossed a threshold from which there was no immediate return. The moment that threshold was crossed, the point at which permanent ice began to accumulate on Antarctica for the first time in tens of millions of years, is recorded in the geological record with remarkable clarity, marking what scientists refer to as the Eocene-Oligocene transition, or EOT, approximately 34 million years ago. And the oxygen isotope record preserved in the shells of benthic foraminifera from deep-sea sediment cores provides the most continuous and globally coherent record of this transition. Oxygen exists in two stable isotopic forms, oxygen-16 and oxygen-18, whose relative proportions in seawater change as ice accumulates on land. When water evaporates from the ocean and falls as snow, it preferentially incorporates the lighter oxygen-16 isotope. As this water is locked into growing ice sheets rather than returning to the ocean, the remaining seawater becomes progressively enriched in oxygen-18. Organisms building their shells from seawater record this isotopic shift, and the shells they leave behind in marine sediments preserve it across geological time. At the Eocene-Oligocene boundary, sediment cores from ocean basins worldwide show a sharp and substantial increase in oxygen-18 values, a signal interpreted as reflecting both the cooling of deep ocean waters and the rapid accumulation of ice on Antarctica. This isotopic shift, known as the EOT isotope excursion, is one of the most distinctive features in the Cenozoic paleoclimate record. The causes of this transition are understood through a convergence of geological, geochemical, and modeling evidence, and they involve several interacting mechanisms operating across different timescales. The long-term decline in atmospheric carbon dioxide concentrations across the Eocene, driven by enhanced silicate weathering and changes in organic carbon burial, had progressively reduced the greenhouse forcing maintaining global warmth. By the late Eocene, carbon dioxide concentrations had fallen to levels at which climate models indicate the Antarctic ice sheet could begin to nucleate, to form and sustain itself against the seasonal warming that would otherwise melt seasonal snowfall. Proxy reconstructions of atmospheric carbon dioxide across the Eocene-Oligocene boundary, derived from the boron isotope compositions of marine carbonates and the carbon isotope signatures of ancient soils, consistently indicate a decline in carbon dioxide concentrations coinciding with the onset of Antarctic glaciation, supporting the interpretation that greenhouse gas drawdown was a primary driver of the transition. Tectonic reorganization of ocean gateways played a complementary and closely debated role in the cooling transition. The opening of the Drake Passage between the southern tip of South America and the Antarctic Peninsula, allowing the establishment of the Antarctic circumpolar current, has long been considered a key factor in the thermal isolation of Antarctica. By permitting a continuous eastward-flowing current to encircle Antarctica without interruption by continental landmasses, the Antarctic circumpolar current effectively reduced the transport of warm subtropical water to high southern latitudes, allowing Antarctica to cool progressively and accumulate ice. The precise timing of the Drake Passage opening relative to the onset of Antarctic glaciation has been a subject of ongoing scientific debate, with some studies placing its initial opening earlier in the Eocene and others suggesting it was not fully developed until after glaciation had already begun. Current evidence suggests that the opening of the Drake Passage contributed to the conditions favoring glaciation, but was likely not sufficient on its own, operating in conjunction with the declining carbon dioxide trend rather than as a singular cause. The Tasman Gateway, the oceanic passage between Australia and Antarctica, also widened progressively during the Eocene as Australia moved northward away from Antarctica. This widening similarly contributed to the developing circumpolar circulation pattern and the thermal isolation of the Antarctic continent. The combined effect of these two gateway changes, operating across the same broad interval as the carbon dioxide decline, it produced a convergence of forcing factors that collectively pushed the climate system toward the glaciation threshold. The ice sheet that formed on Antarctica at the Eocene-Oligocene boundary was not a gradual, incremental accumulation. Evidence from sediment cores and ice-rafted debris records suggests that the initial glaciation of Antarctica may have proceeded relatively rapidly in geological terms, over perhaps 100,000 years or less, once the threshold conditions were met. This rapidity reflects the operation of positive feedbacks within the climate system. As ice began to accumulate, its high reflectivity reduced the amount of solar energy absorbed by the Antarctic surface, cooling the region further and allowing more ice to form. This ice albedo feedback, operating in the opposite direction from the warming feedback that had helped maintain the ice-free Eocene climate, accelerated the transition once it began. The consequences of Antarctic glaciation extended well beyond the southern polar region. The formation of a large ice sheet on Antarctica locked up substantial quantities of water that had previously been in the ocean, lowering global sea levels. Estimates of sea level fall associated with the initial Eocene-Oligocene glaciation range from approximately 30 to 70 meters, reflecting the uncertainty in reconstructing the volume of the early Antarctic ice sheet. This sea level drop exposed previously submerged continental shelves, altered coastal configurations, and drained the shallow epicontinental seas that had covered large portions of continental interiors during the warm Eocene. Terrestrial environments that had been marine were returned to land, reshaping the geographic distribution of habitats available to terrestrial organisms. Ocean circulation was profoundly reorganized by the developing Antarctic ice sheet and the associated cooling of southern ocean waters. The formation of cold, dense bottom water around Antarctica, Antarctic bottom water, established a new mode of deep ocean circulation driven by the sinking of cold polar water, replacing the more sluggish, thermally homogeneous deep circulation of the warm Eocene ocean. This reorganization increased the ventilation of the deep ocean, raising oxygen levels in deep water environments and altering the chemistry and biology of the ocean floor across the globe. The modern pattern of thermohaline circulation, in which cold water sinks at high latitudes and spreads along the ocean floor, has its origins in this Eocene-Oligocene reorganization of the deep ocean. The atmospheric consequences of the cooling transition included a strengthening of the meridional temperature gradient, the difference in temperature between the equator and the poles, as polar regions cooled relative to the tropics. This strengthened gradient intensified atmospheric circulation, producing stronger and more defined jet streams, more pronounced seasonal temperature contrasts at mid-latitudes, and a reorganization of global precipitation patterns. Environments that had been broadly humid during the Eocene began to experience more pronounced seasonality, and the latitudinal boundaries of vegetation zones shifted progressively toward the equator as the thermal conditions supporting high-latitude forests declined. The formation of the Antarctic ice sheet at the Eocene-Oligocene boundary represented the end of the last sustained ice-free period in Earth's history, but it did not immediately produce the fully glaciated planet that exists today. The initial glaciation of Antarctica was a beginning, the first permanent establishment of large-scale continental ice in tens of millions of years, and its consequences unfolded progressively across the Oligocene, Miocene, and Pliocene epochs as the ice sheet waxed and waned, as the Arctic slowly cooled, and as the global climate system reorganized itself around a new set of boundary conditions defined by the presence of permanent polar ice. Understanding the first ice age requires examining not just the moment of ice sheet formation, but the cascading sequence of changes that its existence set in motion across the ocean, the atmosphere, and the biological communities of both hemispheres. The Antarctic ice sheet that formed at the Eocene-Oligocene boundary was not identical in its extent or character to the ice sheet that covers Antarctica today. Paleoglaciological reconstructions based on sediment core records, glacial erosion surfaces, and ice-rafted debris distributions suggest that the early Oligocene ice sheet was dynamic, expanding during cooler intervals and retreating during warmer ones, rather than the relatively stable feature it eventually became. Ice-rafted debris, then the coarse sediment transported by icebergs carving from marine terminating glaciers and deposited on the ocean floor as the icebergs melt, appears in southern ocean sediment cores beginning at the Eocene-Oligocene boundary, providing direct physical evidence of glacial ice reaching the Antarctic coastline and producing icebergs capable of transporting sediment into the open ocean. The distribution and composition of this ice-rafted material allows paleoceanographers to reconstruct the approximate extent and timing of early Antarctic glacial advances and retreats with considerable precision. The influence of the growing Antarctic ice sheet on global ocean circulation was immediate and far-reaching. As described in the context of the cooling transition, the formation of cold and dense Antarctic bottom water established a new mode of deep ocean circulation whose effects propagated through every ocean basin. Cold bottom water spreading northward along the ocean floor from Antarctica displaced the warmer, less dense deep water of the Eocene Ocean, progressively cooling the deep sea across the globe. This cooling of the deep ocean is recorded in the oxygen isotope and magnesium to calcium records of benthic foraminifera from sediment cores across the Atlantic, Pacific, and Indian Oceans. A globally coherent signal of deep ocean cooling following the Eocene-Oligocene transition. The reorganization of deep ocean circulation also had consequences for the distribution of nutrients, the patterns of biological productivity in surface waters, and the chemistry of the carbonate system regulating ocean pH and carbonate preservation. Sea level changes associated with the early Oligocene glaciation reshaped the physical geography of every continent. The withdrawal of shallow epicontinental seas that had covered large areas of continental interiors during the Eocene exposed extensive new land surfaces. In North America, the shallow sea that had occupied portions of the Gulf coastal plain and extended northward into the continental interior retreated significantly. In Europe, the epicontinental seas that had covered much of the low-lying northern and central regions receded, exposing new terrestrial environments. These newly exposed continental surfaces were initially colonized by vegetation and terrestrial organisms tracking the available habitat. But the changing thermal and hydrological conditions of the early Oligocene meant that the environments available to colonizing organisms were fundamentally different from the warm, humid Eocene landscapes that the retreating seas had previously covered. The terrestrial consequences of the initial glaciation extended well beyond the simple withdrawal of epicontinental seas. The strengthening of the meridional temperature gradient that accompanied Antarctic glaciation drove a reorganization of atmospheric circulation that altered precipitation patterns across the mid-latitudes. Evidence from paleosol chemistry, fossil pollen assemblages, and sedimentary facies from Oligocene continental deposits indicates a general trend toward increased seasonality, and in some regions, increased aridity compared to the broadly humid conditions of the Eocene. The dense, moisture-rich forests that had characterized mid- and high-latitude Eocene landscapes began to open, fragment, and in some regions give way to more seasonal woodland or early grassland precursor environments. This vegetational shift, tracking the changing thermal and hydrological conditions of the cooling Oligocene world, had profound consequences for the terrestrial faunas dependent on forest habitats. The cooling of surface waters in the Southern Ocean and at progressively lower latitudes drove changes in marine biological communities that are clearly recorded in the microfossil record of Oligocene marine sediments. Warm water planktonic organisms that had thrived across broad latitudinal ranges during the Eocene declined in diversity and geographic extent as surface temperatures fell. Cold water adapted species diversified in their place, particularly in the Southern Ocean, where the developing circumpolar circulation established a new, thermally distinct oceanographic province. The diversification of cold water marine communities during the Oligocene laid the biological foundation for the rich polar marine ecosystems that characterize the Southern Ocean today. Ecosystems whose existence depends entirely on the cold, nutrient-rich conditions produced by the Antarctic circumpolar current and the upwelling it drives. The Arctic region, during the early Oligocene, had not yet developed the permanent ice cover that characterizes it today. The formation of a significant Arctic ice sheet was a later development, associated with further cooling during the Pliocene and the intensification of Northern Hemisphere glaciation approximately 2.6 million years ago. During the Oligocene, the Arctic was cooling relative to its Eocene state, and seasonal sea ice may have been forming during winter months at high northern latitudes. But the year-round ice cover of the modern Arctic Ocean did not yet exist. And this asymmetry between the glaciated south and the still relatively open north produced a global climate system quite different both from the fully ice-free Eocene and from the fully bipolar glaciation of the Pleistocene, a transitional state in which one polar region was glaciated, while the other retained a degree of warmth that maintained significant differences in climate between the two hemispheres. The orbital forcing of glacial cycles, the influence of periodic variations in Earth's orbit and axial tilt on the distribution of solar energy across the planet, became increasingly significant as the climate system cooled and ice sheets became established features of the planetary surface. The Milankovitch cycles, which describe the approximately 100,000-year eccentricity cycle, the 41,000-year obliquity cycle, and the 23,000-year precession cycle, modulate the amount and distribution of solar radiation reaching different latitudes at different times of year. These orbital variations had always been operating, but their influence on global climate became amplified once large ice sheets existed to respond to the resulting changes in solar forcing. The growth and retreat of ice sheets in response to orbital forcing, glacial and interglacial cycles, became an increasingly prominent feature of Earth's climate variability across the Oligocene and into subsequent epochs, producing the cyclical pattern of ice advance and retreat that dominates the climate record of the past several million years. The First Ice Age, understood as the initial establishment of permanent continental glaciation following the long ice-free Eocene, there was therefore not a single event, but the opening of a new climatic regime, one defined by the presence of ice as a permanent and dynamically active component of the Earth system. The conditions that had sustained the ice-free world for tens of millions of years had been progressively dismantled by the slow operation of geological and atmospheric processes, and the threshold once crossed, the feedbacks maintaining the new glaciated state proved as self-sustaining as those that had maintained the warmth of the Eocene. The transition from the warm, productive environments of the Eocene to the cooler, more seasonal world of the Oligocene and beyond did not leave the biological communities of the ice-free world unchanged. The ecosystems that had developed across tens of millions of years of sustained warmth, the high-latitude forests, the broadly distributed subtropical marine communities, the diverse megafaunal assemblages of both terrestrial and marine environments, were structured around thermal and ecological conditions that were now being progressively withdrawn. The consequences for the organisms dependent on those conditions were varied and, in many cases, severe. Some lineages adapted, shifted their ranges, or evolved morphological and physiological responses to the changing environment. Others declined in diversity and geographic extent, and some, unable to track the pace of environmental change or find refuge in the remaining warm environments, went extinct entirely. The concept of extinction in response to climate change is often framed in terms of sudden catastrophe, a rapid environmental shift overwhelming unprepared organisms. The transition from the Eocene to the Oligocene was not, in the main, that kind of event. It was a prolonged process operating across millions of years, and the biological responses to it were correspondingly gradual in many cases. Nevertheless, the cumulative effect of sustained cooling, changing vegetation, shifting ocean conditions, and declining habitat availability across the Eocene-Oligocene boundary produced what paleontologists recognize as a significant faunal turnover event, a period during which the composition of biological communities changed substantially, with some taxa disappearing from the record and others expanding or diversifying in their place. Among the most clearly documented casualties of the Eocene-Oligocene transition were the large herbivorous mammals, whose body plans and dietary requirements had been calibrated to the dense, productive forests of the warm Eocene world. The Brontotheres, The large perissodactyls that had reached considerable body sizes by the late Eocene disappeared from the fossil record at or near the Eocene-Oligocene boundary. Their extinction appears to be linked to the decline of the soft-leaved, high-productivity forest vegetation on which they depended. As Eocene forests opened and became more seasonal, the specific plant communities supporting large browsers with relatively unspecialized dentition contracted. Brontotheres, having evolved their large body sizes and dietary requirements within the context of Eocene forest productivity, appear to have lacked the dietary flexibility to adapt to the changing vegetation. Their disappearance from the fossil record coincides with the broader vegetational transition at the Eocene-Oligocene boundary, suggesting a direct causal link between the loss of their preferred habitat and their extinction. The Euanthatheres, the large knobbed herbivores of the North American Eocene, had already declined through the late Eocene before disappearing entirely near the boundary. Their extinction followed a pattern similar to that of the Brontotheres, large, specialized herbivores losing the productive forested environments that had sustained their ecological requirements. The pattern across multiple large herbivore lineages is consistent with a general principle observed in subsequent extinction events. Large-bodied, ecologically specialized organisms are disproportionately vulnerable to habitat change because their energetic requirements are high, their reproductive rates are low, and their ability to shift dietary preferences or geographic ranges in response to environmental change is constrained by their specializations. Marine ecosystems experience their own restructuring across the Eocene-Oligocene transition, but the warm water marine communities that had extended to high latitudes during the Eocene, coral reef systems, diverse assemblages of warm water foraminifera, subtropical fish and invertebrate communities, contracted toward the tropics as surface temperatures fell. This contraction is recorded in the biogeographic distributions of marine taxa across the transition. Warm water species that appear in mid and high latitude, Eocene deposits are absent from Oligocene deposits at the same sites, replaced by taxa tolerant of cooler conditions. The diversity of some marine invertebrate groups declined at higher latitudes, while cold water adapted lineages diversified in the newly established cool oceanographic provinces of the developing Southern Ocean and the cooling North Atlantic. The Archaeocete cetaceans, the elongated, serpentine early whales such as Basilosaurus, did not survive into the Oligocene. Their disappearance from the fossil record at the end of the Eocene coincides with the appearance and diversification of the two modern cetacean suborders, the Odontocetes, or toothed whales, and the Mysticetes, or baleen whales. This transition represents one of the most significant evolutionary reorganizations in marine mammal history. The Mysticetes, in particular, evolved a feeding strategy, filter feeding using baleen plates to strain enormous quantities of small prey from the water, that would prove extraordinarily well suited to the cold, upwelling-rich, nutrient-dense marine environments produced by the developing Antarctic circumpolar current and the reorganized ocean circulation of the post-Eocene world. The evolution of baleen feeding can be understood, in part, as a biological response to the new oceanographic conditions created by the onset of glaciation, a dietary innovation that unlocked access to the enormous concentrations of krill and small fish, supported by cold, productive polar and subpolar waters. Among terrestrial predators, the creodont lineages that had dominated the large predator guild through the Eocene and into the Oligocene faced increasing competition from the diversifying carnivorans, the lineage that includes all modern terrestrial mammalian predators. Early carnivorans had been present throughout the Eocene as small to medium-sized predators. But across the Oligocene and Miocene, they diversified in body size and ecological specialization, eventually producing the large cursorial and ambush predators that would come to dominate terrestrial predator guilds. The creodonts declined progressively across this interval, their last representatives disappearing from the fossil record during the Miocene. The reasons for creodont decline relative to carnivoran expansion are not fully resolved, but differences in brain size, dental morphology, and locomotor efficiency between the two groups have been proposed as contributing factors, with carnivorans potentially better equipped to exploit the changing ecological conditions of a cooler, more open world. The high-latitude forests that had characterized the Eocene polar regions retreated progressively equatorward as temperatures declined through the Oligocene. The diverse, frost-sensitive plant communities documented from Eocene high-latitude deposits were replaced by more cold-tolerant vegetation assemblages, and eventually, as cooling continued into the later Cenozoic, by the tundra, boreal forest, and ultimately glacial environments that characterize high latitudes today. The animal communities dependent on those forests, the insects, birds, mammals, and reptiles, occupying the ecological roles supported by warm, productive high-latitude vegetation, contracted their ranges accordingly, with some lineages tracking the retreating forest edge and others failing to do so. What the biological record of the Eocene-Oligocene transition ultimately documents is not simply a list of extinctions and survivors, but a fundamental reorganization of life's distribution and ecological structure across the planet. A reorganization driven by the withdrawal of the thermal and ecological conditions that had sustained the ice-free world's characteristic communities for tens of millions of years. The giants of that world, the Brontotheres, the Wintotheres, the Basilosaurids, the high-latitude forests, and their associated faunas, were not eliminated by a single catastrophic event. They were progressively displaced by the slow retreat of the conditions that had made them possible. The ice-free world documented across the preceding chapters of this account is not purely a matter of geological history. It is also, in a measurable and scientifically grounded sense, a matter of potential future. The conditions that produced the warm, ice-free climates of the Eocene were not the result of processes unique to that period of Earth's history. They were the product of physical and chemical relationships between atmospheric carbon dioxide concentrations, global temperature, ice sheet stability, and ocean circulation that remain operative today. Understanding whether Earth could return to an ice-free state requires examining those relationships in the context of both the deep past and the present trajectory of the planet's climate system. The most fundamental parameter governing the stability of Earth's ice sheets is atmospheric carbon dioxide concentration. The paleoclimate record is unambiguous on this point. Sustained periods of high carbon dioxide have consistently corresponded with warm, reduced ice or ice-free climates, while sustained periods of low carbon dioxide have corresponded with glaciated states. The Eocene's ice-free conditions were maintained by carbon dioxide concentrations estimated at between 500 and over 1,000 parts per million. The glaciation of Antarctica at the Eocene-Oligocene boundary occurred as carbon dioxide concentrations declined toward a threshold estimated by climate models at approximately 600 to 750 parts per million, the level below which permanent Antarctic ice sheets could nucleate and sustain themselves against seasonal melting. These figures, derived from multiple independent proxy methods and supported by general circulation model simulations, establish a quantitative framework within which the question of future ice-free conditions can be evaluated. Current atmospheric carbon dioxide concentrations, as of the early decades of the 21st century, stand at approximately 420 parts per million, already substantially elevated above the pre-industrial value of roughly 280 parts per million, and rising at a rate that has no precedent in the ice core record extending back 800,000 years. The rate of carbon dioxide increase currently being driven by fossil fuel combustion, land use change, and industrial processes is orders of magnitude faster than the geological processes: volcanic outgassing, organic carbon burial, a silicate weathering that regulated atmospheric carbon dioxide across the Eocene and the subsequent cooling transition. This rate disparity is itself significant. The climate system's response to carbon dioxide forcing involves feedbacks that operate across a range of timescales, and the rapidity of current forcing means that some longer timescale feedbacks, including changes in ice sheet volume, vegetation distribution, and deep ocean circulation, have not yet fully expressed themselves in the observed temperature and sea level record. Climate models projecting the consequences of continued carbon dioxide increase indicate that, under high emission scenarios, global mean temperatures could rise by 4 to 6 degrees Celsius or more above pre-industrial values by the end of this century. These projections do not yet approach the 10 to 15 degrees Celsius warming of the early Eocene climatic optimum, but they represent a substantial and rapidly achieved departure from the climatic baseline within which human civilization developed. More relevant to the question of ice sheet stability are the longer-term commitments embedded in current carbon dioxide levels. Even if emissions were to cease entirely, the carbon dioxide already added to the atmosphere would continue to exert a warming influence for centuries to millennia as the climate system slowly equilibrates and longer timescale feedbacks, including the slow response of ice sheets and deep ocean temperatures, fully manifest. The stability of the Antarctic ice sheet under elevated carbon dioxide concentrations is a subject of active and intensive scientific research. Current evidence indicates that portions of the West Antarctic ice sheet are already experiencing accelerated melting, driven by the intrusion of warm ocean water beneath floating ice shelves, a process that does not require atmospheric warming to reach the ice surface directly, but instead attacks the ice sheet from below through ocean heat transport. The East Antarctic ice sheet, which contains the majority of Antarctic ice volume, and whose full melting would contribute approximately 52 meters to global sea level, is considered more stable on shorter timescales, but is not immune to the effects of sustained warming. Paleoclimate evidence from the Pliocene epoch, approximately 3 million years ago, when carbon dioxide concentrations were last comparable to present values at around 400 parts per million, suggests that sea levels were 10 to 25 meters higher than today, implying substantially reduced ice sheet volumes under carbon dioxide concentrations similar to those currently observed. The question of whether Earth could become fully ice-free, returning to a state analogous to the Eocene, is therefore not a question of physical impossibility. It is a question of the carbon dioxide concentrations sustained over sufficient timescales. The paleoclimate record demonstrates that ice-free conditions are a documented and repeatable state of the Earth system, accessible under the right combination of greenhouse gas forcing and tectonic boundary conditions. The tectonic configuration of the present Earth differs from that of the Eocene. The Drake Passage is open, the Antarctic circumpolar current exists, and the thermal isolation of Antarctica is more complete than it was during the early Eocene, meaning that the carbon dioxide threshold required to fully deglaciate Antarctica under present tectonic conditions may be somewhat higher than the concentrations that maintain the Eocene ice-free state. Current model estimates suggest that full deglaciation of Antarctica would require sustained carbon dioxide concentrations substantially above present values, potentially in the range of 1,000 parts per million or higher, maintained over timescales of thousands to tens of thousands of years. The timescales involved in ice sheet response distinguish the near-term future from the deep future in important ways. On the timescale of centuries, the primary concern is partial ice sheet loss, the accelerated melting of vulnerable ice sheet sectors, producing sea level rise measured in meters rather than tens of meters. On the timescale of millennia, sustained elevated carbon dioxide concentrations could drive more complete deglaciation, with sea level consequences approaching those of the Pliocene warm intervals. On the timescale of tens of thousands of years and beyond, the trajectory depends on the long-term carbon cycle balance, the interplay between the carbon dioxide added by human activity and the geological sinks that will eventually draw it back down. What the deep history of Earth's climate system ultimately demonstrates is that the planet's ice-covered state is not a permanent condition, but a phase, one defined by specific atmospheric, tectonic, and orbital conditions that have prevailed for the past 34 million years, but that represent only a fraction of the planet's total climatic history. The ice-free world of the Eocene was real, well documented, and sustained across tens of millions of years. The processes that ended it were slow, geological, and operating on timescales far beyond human experience. The processes now potentially reversing the long cooling trend are rapid, measurable, and occurring within the span of human generations. Whether those processes will ultimately drive the climate system back across the threshold into an ice-free state, and across what timescale, remains one of the most consequential questions in contemporary Earth science.